Our whole part of the galaxy is moving toward something we can't see. There's a hidden force out there. Astronomers call it the Great Attractor, and it's pulling us, the Milky Way, and thousands of other galaxies toward one spot in space. So we'll look at what this mystery actually is, how finding it changed where we think we are in the cosmos, and for a long time we couldn't see it. There was too much dust in the way. But its gravity is huge. It tells us something about the structure of things, the structure we can't see. It's a strange feeling, knowing your home is falling. Falling toward a center you can't even find. It started with a map of the oldest light we can see. That's the cosmic microwave background, the leftover glow from the Big Bang. A picture of the universe when it was just 380,000 years old. For a long time, everyone thought this light would be perfectly smooth. The same in every direction, a kind of a final backdrop, a reference frame. But in the early 70s, a team was looking at data from instruments mounted on U2 planes. And they saw it wasn't smooth. The map had a pattern. Toward the constellation Leo, the radiation was a tiny bit warmer, a hot spot, and exactly opposite toward Aquarius, it was a tiny bit cooler. A cold spot. This pattern had a name, the dipole anisotropy, and it wasn't a mistake. It meant we were moving, not just our planet or our sun, our entire local group of galaxies. All of it, the Milky Way, Andromeda, the smaller ones, was rushing through that backdrop. The speed was 600 kilometers per second, over 2 million kilometers an hour. So the question was right there. What was pulling us? What force could grab our whole galactic neighborhood and drag it that fast? That map of ancient light, it became a clue. A starting point. The hunt was on. That speed was only part of it, because to really understand the pull, you had to separate two things happening at the same time. One is the expansion of the universe. That's the stretch of space itself, carrying all the galaxies apart, like dots on a balloon that's inflating. And the other is what's called a peculiar velocity. That's a galaxy's own motion, its personal drift, like a fish swimming in a river against the current or with it. And that motion we saw, the 600 kilometers per second, that was the total. The expansion plus our own peculiar drift. So the hard part was pulling them apart. Astronomers needed to map not just where galaxies were, but how they were moving on their own. And that meant meticulous work. There was a key project, the H.I. Parkes All-Sky Survey. They used a big radio telescope in Australia. They weren't looking for stars. They were listening for the faint signal from neutral hydrogen gas. It's the most common element, and it fills spiral galaxies. By measuring the exact frequency of that radio hum, they could figure out how fast thousands of galaxies were moving toward us or away. Separate from the universe's expansion, it was like a galactic census, getting not just addresses but the exact speed of every home. And when they plotted all that data, a pattern showed up. It wasn't chaos. Across a huge volume of space with thousands of galaxies, the individual motions weren't random. They were aligned, like iron filings near a magnet. These galaxies had a coherent flow, a great river of star systems all streaming the same way. That river was flowing toward Centaurus and Hydra, a part of the sky hidden behind the dust of our own Milky Way. And that was the crucial evidence. The galaxies weren't just riding the cosmic expansion. They were being tugged. Their peculiar velocities were all pointing like compass needles toward one unseen spot. A gravitational sink, something massive hiding behind our galaxy's dust, pulling everything toward it. The ancient light map gave us our speed. This river of galaxies gave us our direction. So now the hunt had a destination. The river of galaxies was pointing somewhere, to a place we couldn't see. All the clues, the velocities, the flow, they all lined up on one patch of sky. But when they looked with optical telescopes, there was almost nothing, just foreground stars, a kind of glowing fog. It wasn't empty, it was a wall. Our own galaxy was in the way. They call it the Zone of Avoidance, this band of dust and gas and stars lying in the flat plane of the Milky Way. It blocks about 20% of the universe outside. Like a window that's frosted over, smeared with paint. You know there's something out there, but the details are gone. For a long time, they thought the Great Attractor was right behind that curtain. A mountain hidden in a permanent fog, and that was the challenge. How do you map what you can't see? How do you study a gravitational monster when your main tool, light, is useless? It forced a change in technique. They had to learn to see in different colors, not colors we see, invisible signatures. They used X-ray observatories to detect the million-degree glow from vast clouds of gas. Where galaxies cluster, they heat that thin gas. It shines in X-rays, and they used radio telescopes, listening for the whisper of hydrogen gas or the jets from supermassive black holes. Those wavelengths cut through the Milky Way's dust, like a scan seeing through skin to the bone. What came out of the data wasn't a void. The hidden zone was full. Early surveys showed hints of huge structures, entire clusters of galaxies back there, never catalogued before. Their light absorbed by our own galaxy. Each detection was like a sonar ping, mapping the seafloor of a hidden ocean. The Great Attractor wasn't one single object. It was probably the heart of something much bigger, a dense knot in the cosmic web, a gravitational anchor so massive it was pulling us, and thousands of others, toward it. The search had shifted from a mystery of motion to a problem of perception. We weren't just feeling the pull anymore. We were starting to glimpse the shadow of the thing doing the pulling. The first thing we found was the Norma cluster, this whole city of galaxies about 220 million light-years out. It was sitting almost directly behind the thickest part of our own Milky Way. And for a moment it seemed like the answer, something that massive could pull on us. The Norma cluster is a rich cluster. Its center is this dense swarm of old, elliptical galaxies, thousands of them packed into a small space. And around that, a huge halo of gas glowing, heated to millions of degrees. That gas sends out powerful X-rays. That's how we saw it finally. That X-ray glow cut through all the dust. It showed this immense, energetic place. The mass of it all, the galaxies and that superheated gas, is just staggering. It's a real gravitational anchor. So it made sense to look at Norma and think, this is the thing. This is the Great Attractor, but the math didn't work. When they calculated it, the gravitational pull from Norma, given its distance and total mass, the numbers came up short. It was powerful, but not that powerful. It couldn't account for the whole flow, the entire river of galaxies we were seeing. The motion of our local group and all the others needed a source of gravity far bigger than Norma. So the cluster wasn't the answer. It was a clue, a signpost. It meant we were looking in the right direction, but the real source was even bigger and even more hidden. Finding Norma was like finding a huge mountain in the fog, and then realizing that mountain is just sitting on the slope of a much larger range, one you still can't see. The search had to go deeper. The search had to go past the mountain. It had to look for the whole mountain range, and as astronomers mapped things on a bigger scale, they looked much deeper into space. Over 650 million light-years away, toward Centaurus, there's the biggest concentration of mass in our local universe. It's called the Shapley Supercluster. The name doesn't really capture it. It's not just a cluster of galaxies. It's a supercluster, a whole continent of galaxies. A normal cluster might have a few hundred galaxies, maybe 1,000. Shapley has dozens of those rich clusters, all held together by gravity. It's a dense, sprawling metropolis of stars and dark matter, so massive it warps space around it for hundreds of millions of light-years. Its gravitational pull is immense. It tugs on everything, including us. So for a while there was this new idea. Maybe this was the real answer. Maybe the great attractor wasn't a single hidden thing, but this distant, undeniable titan. Shapley was so huge it had to be the main force pulling us, but gravity has rules. One big rule is that its strength fades with distance. It fades dramatically. The pull from something gets weaker by the square of how far it is. Something twice as far away only pulls with a quarter of the force. Shapley is over 3 times farther than the Norma cluster, the suspected great attractor region. That distance softens its tidal force on us. Shapley's mass is colossal, but its command over our neighborhood is diluted by all that space in between. That created a puzzle. It wasn't a simple mystery with one culprit anymore. It was a gravitational tug of war. On one side, you have Shapley, the distant behemoth, pulling from far away with its sheer weight. On the other side, you have the hidden mass in the zone of avoidance, the Norma cluster, and whatever else is there, pulling from much closer with a more direct grip. Our motion, the flow of our galaxy river, is the result of both. It's the net effect of these two giants wrestling over our corner of the cosmos. The great attractor wasn't necessarily one or the other. It was likely the combined influence of the nearby mass, with Shapley providing a powerful, steady background pull from the depths. That changed the question. We weren't just looking for a missing object anymore. We were trying to map the balance of power in an invisible war, where gravity is the only soldier and galaxies are the prizes. The invisible war needed a better map. We had to see the battlefield in 3 dimensions, not just where things were on the sky, but how deep they went into space. And the breakthrough came from 2 big projects. The first was the 2-micron all-sky survey. It looked in the infrared, not visible light, like night vision for the universe. Infrared slips right through the dust clouds of our own galaxy. So the frosted window cleared. We could finally see the shapes of galaxies that were hidden behind that wall of stars. It was like turning on the lights in a room we only knew from shadows, but knowing a galaxy's shape and position wasn't enough. We needed its distance. That's where the second project came in, the 2-degree field galaxy Redshift survey. It used an instrument that could capture the light of 400 galaxies at once. And by analyzing that light, it measured each galaxy's redshift. That redshift tells us how fast the galaxy is moving away from us because of the universe's expansion. And that tells us its distance. It's the fundamental tool for building a 3-dimensional map. This survey didn't just look at a few targets. It catalogued the positions and distances of over 200,000 galaxies. Like mapping every major city and town across a continent, and then plotting them in a giant floating model. That's what they did for our local universe. So they combined the data, the infrared views that pierced the dust, and the redshift measurements that gave depth, and the hidden structure snapped into focus. The Great Attractor region wasn't a single monster galaxy. It wasn't even one dominant cluster. It was a vast confluence, a gravitational watershed. Picture a mountain range where several great rivers have their source. This region was like that, but for gravity. It was a dense knot in the cosmic web, a place where several filaments of dark matter and galaxies intersected. Multiple rich clusters like Norma were embedded in it, along with dozens of smaller galaxy groups and immense clouds of hot gas, all of it woven together by gravity into one immense overdensity of mass. This was the source of the pull, not a point but a place, a sprawling gravitational basin where the cosmic flows of our neighborhood naturally converged. Our local group and all the other galaxies in the river were just following the slope of space-time down into this basin. The map finally showed why the math was so complicated. We were being pulled by the combined gravity of an entire landscape. The nearby mass was pulling, and the distant Shapley Supercluster was adding its weight to the tug. So the mystery shifted again from what is pulling us to understanding the architecture of the pull itself. We had a three-dimensional map of the local cosmos. And that brought up a new question. Where do we actually belong? For a long time, we thought our home was the Virgo Supercluster, a collection of galaxy groups with the Virgo cluster at the center. But that definition was mostly about where things were located. It wasn't about how they moved. It was just a snapshot. In 2014, a team of astronomers used that huge river of galactic motion to tell a different story. They looked at the peculiar velocities of over 8,000 galaxies, not just their positions but their flows, and they saw a pattern so large it redefined our place. They called it Laniakea. That's a Hawaiian word for immense heaven. It's our supercluster, a continent of galaxies, about 100,000 of them. Stretching across 520 million light-years, its borders aren't drawn by static geography. They're defined by watersheds in space-time. Like water on Earth flows toward an ocean basin, every galaxy inside Laniakea flows toward a common gravitational center, and that center is the Great Attractor region. So the Great Attractor isn't our final destination. It's the beating heart of our immense celestial home, the core that every member galaxy is streaming toward. Slowly, inevitably, including our own Milky Way, we're not being pulled by some alien external force. We're falling inward toward the center of our own community. That changes our cosmic address. Our galaxy isn't just a lonely island. It's more like a leaf caught in a vast, slow-moving river. That river is the collective motion of Laniakea. All the galaxies around us are on the same journey, flowing down the gentle slopes of gravity toward a common point. We're part of a structure with a dynamic identity, defined by shared motion and a shared fate. To picture it, think of Laniakea not as a rigid sphere, but as a sprawling, fibrous web. Delicate tendrils of galaxies stream along invisible filaments of dark matter. They converge like tributaries into a great river, flowing into the gravitational basin of the Great Attractor. Our local group is on one of those tributaries. We're not at the center, we're out in the suburbs on the far edges of this immense heaven, forever in motion toward its luminous, hidden heart. That's where we live. Not in a static cluster, but within a flowing supercluster, a structure so vast we could only see its true shape when we learned to read the story written in the motion of the stars. Even with Laniakea mapped, the pull is still a strange idea. It's not a magnet grabbing metal. It's more subtle, more profound. To understand the Great Attractor, you have to think about the shape of space. Picture a landscape, a vast, gently rolling landscape, but it's not made of dirt. It's made of space and time. Astronomers call it the cosmic gravitational potential. A star makes a tiny dimple in that landscape. A galaxy makes a deeper bowl, and where matter is concentrated, a cluster of galaxies, a supercluster, a knot in the cosmic web, the dimple becomes a deep well. The fabric of reality is curved there, warped by all that stuff, the stars and the dark matter. The Great Attractor is one of these wells, a local minimum. It's not a point, it's a region, a sprawling basin where space-time tilts inward from every direction. Our galaxy, and every other in Laniakea, is like a marble on that tilted surface. We aren't being pulled by a string, we're rolling downhill, following the curvature carved by the mass of the entire region. That's why it's not about one object's mass. The Norma cluster adds to the slope, the hidden galaxies behind the dust add to it. Even the distant Shapley Supercluster far away adds its own gentle tilt. The pull we measure, that 600 kilometers per second, is just our speed rolling down this universal hillside. It's the gradient, the steepness of the slope. And that changes how you see the journey. We're not being dragged to a finish line. We're flowing like water in a watershed, seeking the lowest point. Every galaxy here is on a similar path, tracing the invisible contours of a shape we can only feel. Our motion is a readout of the hidden architecture of the universe. It says space isn't a flat, empty stage. It's a textured fabric, and we are forever navigating its invisible hills. Even with that map of bright galaxies, the numbers still didn't line up. The visible things, the stars, the glowing gas, the clusters, they aren't heavy enough. They don't have the gravitational strength to explain those powerful flows we observe. If the Great Attractor were only made of the galaxies we can see, that slope in space would be too shallow. Our marble wouldn't roll that fast. There's a huge amount of mass missing from the picture. And that missing mass has a name: dark matter. It's the invisible framework of the cosmos, the hidden structure everything luminous is built on. Think of it like a city at night. You'd see the streetlights, the lit windows. You could map those points of light, but that map wouldn't show you the ground the city sits on, or the steel skeletons inside the buildings. The lights are just where people are. The real structure, the thing holding it all up and giving it shape, is invisible in the glow. Dark matter is that structure for the universe. It doesn't emit, reflect, or absorb light. We can't see it with any telescope, but we know it's there because of its gravity. We see its effects in how galaxies spin too fast to be held together by visible stars alone. We see it bending light from distant objects, gravitational lensing. And on the largest scale, we see it in the motion of superclusters. The Great Attractor isn't mainly a collection of bright galaxies. At its heart, it's a vast concentration of dark matter, a mountain of invisible mass. The galaxies we see, like the Norma cluster, are just the glittering towns on its slopes. They're tracers, little pinpoints of light that happen to mark where this immense, unseen halo is most dense. The gravitational pull we feel, that steep slope, is overwhelmingly from this dark scaffold. It binds the visible clusters into a single, coherent gravitational entity. Without that dark matter halo, those clusters wouldn't be streaming together. They'd drift apart, so the Great Attractor is more than a destination. It's a crucial laboratory. By studying how galaxies move within its grasp, we're indirectly studying the distribution and behavior of dark matter itself. We're measuring the shape and density of an invisible mountain range by watching how rivers flow toward it. Every measurement of a galaxy's peculiar velocity is a data point that helps us chart the contours of the unseen. This changes what we think we're flowing toward. We're not just heading for a spot in the sky marked by brilliant cities of stars. We're falling into the gravity well of a ghost. A vast, silent presence that shapes the cosmos from the shadows, guiding the long-term fate of everything we can see. That dark matter mountain range pulls on us, but it also complicates one of the most important numbers we have. The Hubble constant, the rate the universe is expanding, how fast galaxies are moving apart from each other, and from that, the age of everything, the fate of everything. For decades, the goal has been to pin this number down with perfect precision, but there's a problem. Two of our best methods don't give the same answer. That's the Hubble tension, and the gravity of something like the Great Attractor is right at the center of it. It's like trying to measure the current of a wide, powerful river. If you're in a small boat, you need to know two things: the speed of the river's flow itself, and then any local wind, any eddies pushing your boat sideways. The Hubble constant is the speed of the river, the pure expansion of space. Our boat is any galaxy we use to make the measurement, but the Great Attractor is like a powerful local wind. Its gravity gives our galaxy and all the nearby galaxies we look at an extra motion. That's our peculiar velocity. It's not from the expansion, it's from the local geography of mass. So when astronomers use nearby galaxies or supernova to calculate the expansion rate, they have to do this delicate subtraction. They have to strip away the influence of every local flow, every gravitational tug, including the huge pull from the Great Attractor and from the Shapley Supercluster behind it. Only then can they isolate the true signal, the clean expansion. It's an incredibly difficult correction. We're trying to map the gentle, uniform stretching of space itself, while we're being jostled by these powerful tides from our local neighborhood. Now, the other method, it uses the cosmic microwave background, that ancient light from the infant universe. That light comes from so far away, from a time so early, that local structures like our supercluster didn't exist yet. There were no great attractors, so the expansion rate measured from that distant, pristine signal isn't contaminated by local flows. In theory, it should give us the pure, fundamental Hubble constant. The tension is this: the locally measured rate, after all our careful corrections for the great attractor's pull, still comes out a bit faster than the rate from the distant cosmic background. The numbers don't match. It's as if the river's current is measurably stronger here and now than it was at its source, and this isn't a small error, it's a persistent gap. It's survived years of better and better observations. What it means is something's off. Either our corrections for local flows are still incomplete, that there are even larger, unseen masses tugging on us, or there's something we don't understand about the physics of the universe itself. Maybe dark energy isn't constant, maybe it's changing over time, so the great attractor, this local mystery of motion, has become a key piece in a global crisis. It reminds you that to see the universe clearly, you have to understand your own place within its invisible architecture. The Hubble tension makes us check our own local measurements. We have to be sure our corrections for the pull are right, and that means seeing what's hidden. To map the great attractor, you have to look right through the Milky Way. So how do you study something behind a curtain of stars? You don't use just one kind of light. You listen and look in every way you can, building a picture from invisible signatures. X-ray observatories are the first tool. Space telescopes like Chandra and XMM Newton, they don't see stars, they see heat, immense heat. Where galaxies cluster, the thin gas between them gets squeezed. Heated to millions of degrees, it glows in X-rays. That's how we first truly saw the Norma cluster. Its core is a beacon of X-ray light, cutting straight through the optical fog of our galaxy's disk. That hot gas halo tells you the cluster's mass, its density, its gravitational footprint. It shows the energetic heart of these hidden structures. Then there are radio telescopes. Instruments like the Parkes telescope in Australia and the Future Square Kilometre Array, they listen. They tune into the faint radio hum from neutral hydrogen gas. It's the most common element, and it fills spiral galaxies. By mapping where this hydrogen is and how it's moving, radio astronomers can trace the shapes of galaxies completely hidden in visible light. They can find whole new clusters, their presence given away by this quiet cosmic whisper. Radio waves pass through the dust of the Milky Way as if it weren't even there. For cooler, dust-shrouded objects, we use infrared. Space telescopes like Spitzer and WISE. Infrared light has a longer wavelength than visible light. It doesn't get scattered by tiny dust grains. It sails right through. So an infrared view of the zone of avoidance changes everything. The glowing fog of our galaxy becomes transparent. Behind it, the faint, reddened shapes of countless distant galaxies emerge. You see their structure, their distribution. You see the backbone of the cosmic web previously masked. Each tool gives a different piece. X-rays show the hot, energetic plasma in the densest gravitational wells. Radio waves map the cool, raw material of galaxies themselves. Infrared reveals the stellar populations shrouded in dust. Combine these views, and you build a three-dimensional portrait of the hidden mass. We're not looking with our eyes anymore. We're assembling a picture from echoes of heat, whispers of gas, the glow of buried stars. It's a kind of cosmic synesthesia, translating invisible signals into a map of the gravitational landscape we're falling into. The hidden landscape we're mapping, it isn't unique. It's a prediction. To understand that, you build a universe from scratch, not with telescopes, with mathematics and silicon. Cosmologists run immense computer simulations for this. They're called N-body simulations. The N is for the number of particles, and that number is staggering. Billions of particles, trillions, each one representing a parcel of dark matter. The goal is simple in concept. You start with the conditions of the early universe, just after the Big Bang. A nearly smooth soup of matter and energy, seeded with the tiny ripples we see in the cosmic microwave background. Then you press play. Let gravity do its work over billions of years of simulated time. The most famous of these is the Millennium simulation. It used over 10 billion particles. It traced the evolution of dark matter in a cube of simulated space, over 2 billion light-years on a side. It ran on a supercomputer for an entire month, and what emerged from that digital dawn was breathtaking: a cosmic web, a vast, intricate network of filaments and voids. Where the dark matter particles clustered under their own gravity, they formed dense knots. Those knots became the sites where galaxies would later form. The filaments connected them like threads in a three-dimensional spiderweb, and at the intersections of the thickest filaments, immense clusters and superclusters naturally coalesced. In these virtual universes, something else happens. The simulated galaxies, those clumps of particles, they begin to move. They stream along the filaments. They flow toward the densest knots, the intersections. They form great rivers of motion, converging on gravitational centers. When scientists analyze the velocity fields in these simulations, they see patterns identical to what we observe. They see coherent flows. They see simulated superclusters with all their member galaxies drifting toward a common heart. They see, in essence, great attractors. Not by design, by the inevitable mathematics of gravity acting on a slightly lumpy universe. This is the profound validation. The great attractor is not an anomaly. It's a feature, a predicted outcome of how cosmic structure grows. By comparing these digital universes to our painstakingly assembled maps of the real one, scientists can test theories. They can ask, if dark matter behaves this way, do we get structures that look like Laniakea? Do the flows match the speed we measure? The answer so far is yes. The simulations tell us that what we are experiencing, our long fall toward the hidden basin, is the standard story for a galaxy like ours. We are living inside a process that the equations foretold. Our motion is a single data point in a universe of simulated motions, all telling the same tale of an evolving, structured cosmos. Let's look at this neighborhood. The Norma cluster is the first city you'd reach, the closest major cluster, but just a bit farther out in the direction of Centaurus, there's the Centaurus cluster. It's another immense gathering, slightly farther away than Norma, but incredibly rich. At its heart is Centaurus A, a famous radio galaxy with colossal jets erupting from its supermassive black hole, spewing energy across space. This cluster is turbulent, adding its own significant weight to the gravity well. Then there's the Hydra cluster further out still. It's one of the most massive clusters we know of in our local universe. Its center is dominated by giant elliptical galaxies, ancient cities of stars that have cannibalized their neighbors over billions of years. The sheer number of galaxies in Hydra and the vast reservoir of superheated gas between them makes it a gravitational anchor of immense power. But perhaps the most telling structure is the core of the Great Attractor itself. Astronomers label it Abell 3627. This isn't just a cluster. It's a scene of cosmic collision. 2 or even 3 massive galaxy clusters are merging here. It's chaotic, violent, on a scale we can barely comprehend. Galaxies are whipped around like leaves in a hurricane, and the gas between them is heated to hundreds of millions of degrees, creating some of the most intense X-ray emissions we can detect. This titanic merger represents a huge concentration of mass, right in the predicted heart of the Attractors basin. So the gravity we feel isn't from one of these clusters. It's from all of them, and crucially, it's also from everything in between. The thousands of smaller galaxy groups, the lonely spiral galaxies drifting along the filaments. And most of all, the vast, diffuse ocean of dark matter that envelops this entire region, binding these glittering clusters into a single, coherent gravitational entity. The Great Attractor is this collective, the sum of these parts. It's the entire watershed, not just the deepest lake. Our journey isn't toward a single point of light, but into the embrace of a crowded, dynamic, and largely invisible metropolis of mass. We're headed toward the Great Attractor, but we won't ever get there. It's not a straight fall. It's more like a huge, slow orbit, like the planets around the Sun. The Sun pulls them in, but they don't fall in. They have sideways motion. That sideways velocity balances the pull, so they circle, they stay in stable paths. Something like that is happening to us, to our galaxy inside Laniakea. We have this inward flow, this movement down the slope, but we also have a lot of sideways motion. A velocity that's perpendicular to the pull. Astronomers measure it. It's significant. So the best model now isn't that we'll plunge into the Norma cluster or into the heart of Abell 3627. Instead, our Milky Way, the whole local group, will probably orbit. We'll orbit the gravitational center of the supercluster. We'll sweep around the Great Attractor basin in an orbit so enormous, so slow, that one circuit takes tens of billions of years. We're not a marble dropping into a well. We're a satellite beginning a lazy cosmic circle around something hidden. But even that orbit sits inside a larger current, the expansion of the universe. And that expansion isn't steady anymore. It's accelerating. A force we call dark energy is stretching space itself. Its influence grows as the universe gets bigger and emptier. On the scale of Laniakea, for now, gravity wins. The pull of all that mass, the dark matter, the galaxies, it's strong enough to hold the supercluster together. Against the stretching, it creates this local inflow, this river of galaxies, but dark energy acts on the largest scales. In the far, far future, its push will overcome gravity's grip. The space between superclusters will stretch so fast that the threads of the cosmic web will snap. Laniakea itself will be carried away by what astronomers call the Hubble flow. The pure expansion of space, it will become an island universe, isolated in a vast and growing sea of nothing. The other superclusters will redshift away. They'll disappear from view entirely. The universe will grow cold, dark, profoundly lonely, so our ultimate fate is layered. In the intermediate future, we orbit. We're part of a grand gravitational dance inside our immense heaven. But in truly deep time, that entire dance floor drifts apart from all others. Our Milky Way's path is a slow spiral inside a structure that's itself becoming a solitary relic. Adrift in an accelerating cosmos, we're flowing toward a center we'll never touch, inside a home that will one day be the only thing left to see. This journey changes how we see ourselves. We are not at the center of anything. We never have been. For most of human history, the cosmos was small, intimate, the ground was still, the sky was a dome. The sun and the stars moved around us. That was the first center we imagined. Then came the revolution. The sun became the center of our solar system. A demotion for Earth, but still a place of privilege. We orbited the great light. Then, a few centuries later, another shift. We realized our sun was just one star. One among hundreds of billions, and it wasn't at the center of the Milky Way. It was out in the galactic suburbs, a quiet spiral arm, another layer of centrality gone. Now we have the Great Attractor. It tells us our entire galaxy, this vast island of stars, is not stationary. It's not even the main gravitational player in its own neighborhood. We are a passenger caught in a flow that encompasses 100,000 galaxies. Our home supercluster has a heart, and we are not it, we are drifting toward it. From the distant outskirts, every time we think we've found our fixed place, a new scale of observation moves us again. It's a relentless lesson, a lesson in cosmic perspective. In humility, we are not the pivot point of creation. We are participants in a motion so vast and slow we can only infer it from the subtle shifts in ancient light. This knowledge can feel disorienting, to realize you are on a speck, flowing down an invisible slope, but it also fosters a different kind of wonder. Not the wonder of being central, the wonder of being connected, of being part of a dynamic, evolving structure, a structure whose full beauty we are only beginning to map. Our trajectory is shaped by the silent gravity of dark matter, by the brilliant fires of distant galaxy clusters, forces utterly indifferent to our existence. Yet they write the long-term story of our celestial neighborhood. We are along for the ride, observing, learning, charting the contours of the immense heaven that carries us. In that act of mapping, we find our place, not at the center, but as witnesses to a grandeur that far exceeds any single point within it. If every supercluster has a gravitational center, then ours can't be the only one. Gravity works the same way everywhere. Wherever you get a huge gathering of matter, it creates a kind of basin, a place where the local flow of galaxies comes together. So the question isn't whether other great attractors exist, it's where we've found them, and the evidence says they're everywhere, each one with its own scale, its own character. There was a discovery a few years back. Astronomers mapping galaxy motions noticed something. In one direction, galaxies were moving away from us faster than cosmic expansion alone would cause. It was like something was pushing them, or really like they were falling toward a great mass on the other side of the sky, leaving an emptiness behind. They called that region the Dipole repeller. It's not a force that repels, it's better seen as a cosmic void, a vast underdense region, a desert with far less matter than average. Gravity works both ways. A mass concentration pulls you in, but a major absence of mass means there's less gravity, they're holding you back, so you effectively flow away from the void. Toward the nearest mass, the dipole repeller is the other side of the great attractor coin. It shows how our motion is shaped not just by what's pulling us, but by what isn't. Then there are structures that match or even exceed our own in scale. Deeper in the southern sky, hidden behind the Milky Way like our attractor, is the Vela Supercluster. For a long time it was just a suspicion, a strange clustering in the redshift data, but new surveys have brought its immense form into focus. It's a colossal wall of galaxies. A filament so vast it challenges what we call a supercluster. Its gravitational pull is enormous, tugging on galaxies across a huge volume. For the galaxies within its grasp, it is their great attractor. Their own gravitational center, these discoveries point to a basic principle. The universe isn't uniform, it's a web, dense clusters and filaments separated by great voids. In that architecture, every major knot, every intersection of filaments becomes a gravitational anchor. Galaxies along those filaments stream toward the knots. They form coherent rivers of motion across hundreds of millions of light years. Our Laniakea Supercluster, flowing toward the Norma region, isn't special in kind. It's one example of a universal process, a process written into the cosmos by gravity and the initial conditions of the Big Bang. In computer simulations of the universe, this is exactly what emerges. Scientists don't program in a single great attractor. They start with a nearly smooth distribution of matter and let physics run. The simulations spontaneously form a cosmic web. And within that web, they show many Laniakeas, many superclusters, each with its own defined basin of attraction, its own set of galaxy flows. The simulated universe is filled with great attractors and dipole repellers. They're inevitable features of a structured cosmos, So the specific arrangement in our neighborhood, the Norma cluster, the Hydra cluster, the Shapley Supercluster, that's unique to us. But the phenomenon isn't. We're living inside a standard piece of cosmic geography, a continent among continents, each with its own hidden heart, guiding the long, slow dance of its galaxies. That realization universalizes our experience. Our journey isn't a solitary mystery. It's the common condition of galaxies everywhere, tracing the invisible contours of the universe's design. Einstein saw space differently. It wasn't just a stage, it was something that could change. General relativity says that mass and energy don't just exist in space. They shape it, they tell space how to bend, and then that bent space tells matter how to travel. That's the language of gravity. It's how you understand something like the Great Attractor. Picture a rubber sheet stretched tight. That's space-time. Put a heavy bowling ball in the middle. The ball sinks, making a smooth depression. That's what the sun does. Then take a marble and roll it across. The marble isn't pulled by a force. It just follows the curve the bowling ball made. Its straight path becomes a circle, an orbit. It's following the shape of the sheet. Now take that idea and make it enormous. Instead of one ball, imagine a whole mountain range of lead on that sheet. A huge, heavy landscape. That's the Great Attractor region. It's not one thing. It's the Norma cluster, the Hydra cluster, Abell 3627, all the hidden galaxies, and the dark matter holding it together. Together, they make a colossal dimple in the cosmos, a basin hundreds of millions of light-years wide. Our galaxy and every galaxy in Laniakea is like that marble. We're not being tugged by a rope, we're following the curve. In relativity, we're traveling along geodesics, the straightest paths through curved space. In flat space, that's a line, but near a huge mass, that straightest path becomes a spiral inward, a flow down into the basin that changes how you see it. The 600 kilometers per second, the River of Galaxies, the fate of our supercluster, it's all just things following the natural shape of reality. The Great Attractor isn't strange. It's what you'd expect in a universe where mass bends the stage. We usually link general relativity to extreme things. Starlight bending around the sun, black holes, GPS clocks, but its deepest show might be its quiet, large-scale work. It operates across the emptiness between superclusters. It's been weaving this cosmic web, setting these great flows in motion for over 13 billion years. So when we measure our galaxy's motion, we're not just tracking speed. We're reading the slope. We're measuring how steep the space-time dimple is that we're rolling down. Every observation of a galaxy's path in Laniakea is a test of Einstein's theory on the biggest stage there is. The Great Attractor, hidden as it is a monument to a simple truth. Matter tells space how to curve, and curved space tells matter how to move. We are the proof of that conversation, written in the slow drift of the stars. The pattern of discovery in astronomy has a rhythm to it. For a long time, the sky was seen as fixed, with Earth at the center of everything. Then Galileo used a telescope. He saw 4 points of light moving around Jupiter. That observation discovered moons, but it also did something else. It broke the old worldview. It proved that not everything circled Earth. So the center we thought we had just vanished. Our place became mobile, adrift in a system with its own rules. Later, centuries later, William Herschel did a different kind of mapping. He counted stars in different directions, trying to trace the shape of our home from the inside. His work gave us the first model of the Milky Way as a flattened disk with our sun near the center. That was another step, another recentering, though we later learned even that center wasn't ours to claim. Today, we have that same curiosity, but our tools are different. They're radio dishes listening to hydrogen, X-ray telescopes seeing million-degree gas, supercomputers simulating universes from the beginning. Our Galileo moment didn't come from seeing new moons. It came from seeing motion, the coherent flow of galaxies, and our Herschel-like mapping used redshift surveys. It plotted positions, but also the three-dimensional watersheds of gravity. That's what revealed the shape of Laniakea. Each revolution follows the same arc. A new instrument reveals a pattern the old models can't explain. That pattern forces a new map. And the new map always moves us. It displaces us from a cherished centrality, first from the center of creation, then from the center of the solar system, then from the center of the galaxy. Now, the great attractor and the structure of Laniakea move us again, from being a stationary island to being a participant in a vast, slow river of stars. This is our current frontier. The great attractor is the mystery on the edge of our latest map. It's the blank space that makes us look harder, to listen in new wavelengths, to question our assumptions about mass and motion. It continues the journey of discovery, not by finding an answer that settles things, but by finding a question that opens up an even grander vista. We're still drawing the lines, still learning the true scale of our home, and in doing so, we're writing the next chapter in the oldest story we know. One of the most persistent images is this giant cosmic vacuum cleaner, a swirling darkness that's going to swallow everything. It's a dramatic story, but it's not what the science says. The great attractor isn't a black hole, not even a supermassive one. The scale is completely wrong. A black hole's gravity dominates a very small region. The great attractor's influence is felt across hundreds of millions of light years. It's a gravitational field, not a singular point. We're not on a collision course with an event horizon. We're flowing toward a broad basin, a gravitational valley, not a bottomless pit. Another idea is that it's pulling the entire universe. That isn't true either. Its influence is immense, but it's local. It governs the motion of galaxies in our Laniakea Supercluster. That's about 100,000 galaxies, and that's a tiny fraction of the observable universe, which holds hundreds of billions. Beyond Laniakea, other superclusters have their own gravitational centers, their own flows. The universe is filled with these basins and watersheds. Ours is just the one we're in. So the cosmos isn't rushing toward one spot. Our particular neighborhood is. This leads to a third point. The great attractor isn't a single object. You couldn't point a telescope at it. You can't land on it. It's a region of space, a confluence of mass. Think of it not as a destination, but as the center of a weather system, a low-pressure zone that draws winds from all around. The winds are the galaxies. The low pressure is the combined gravity of many clusters and vast halos of dark matter. It's a place defined by its collective effect. Finally, there's cosmic expansion. The universe is stretching, carrying galaxies apart. The great attractor isn't pulling us against that expansion. Our motion toward it is a local, peculiar velocity. It's a smaller, specific drift superimposed on that much larger, smoother background flow. Imagine you're on a moving walkway at an airport. The walkway itself is carrying you forward. That's the expansion of the universe. But you can also walk on the walkway. Your walking speed is the peculiar velocity. Our journey toward the great attractor is us walking on the cosmic walkway. The walkway's motion and our own steps are happening at the same time. We are not fighting the expansion. We are moving within it. Clearing away these myths isn't just about correcting facts. It reveals a more subtle reality. The truth is less like a Hollywood catastrophe. It's more like a grand, slow-motion ballet, a dance of galaxies following the gentle curves of space. Shaped by invisible architecture, that story of interconnected motion on a scale we're only beginning to map holds a deeper wonder than any simple tale of doom. Behind every cosmic map, there's a team, people in control rooms staring at screens, going through mountains of data. The great attractor, that wasn't one person's discovery. It was a slow puzzle solved over decades by researchers all over the world. Their stories put a face on it. there's a famous group, the Seven Samurai. In the 80s, 7 astronomers, Sandra Faber, David Burstein, others, they set out to measure how galaxies move. They spent years gathering data, working through the night at remote observatories. They wanted to understand the peculiar velocities of hundreds of galaxies, to see if the motions were random or part of something bigger. The work was painstaking. Long, cold nights at the telescope, calibrating instruments, then months of analysis back at their universities. The signal was buried in noise, in the uncertainties of distance measurements, the complexities of galactic rotation. When their data finally showed a coherent flow, a bulk motion of our whole galactic neighborhood toward one point, that was a eureka, a moment, but it was built on years of quiet work. They had the first strong evidence of the great attractor's pull. Then there's R. Brent Tully, an astronomer whose name is tied to mapping the local universe. For decades, Tully and his colleagues, like Helene Courtois, they've been the cartographers of our cosmic neighborhood. They weren't just plotting points. They were tracing the flows. The work that defined the Laniakea Supercluster involved analyzing the motions of over 8,000 galaxies. Tully talks about the process not as one breakthrough, but as a gradual dawning. A picture emerging from thousands of measurements, like dots connecting, and you only see the shape once the last one is in place. The name Laniakea, immense heaven, that came from wanting to honor the Polynesian navigators. People who understood the stars, the vastness of the Pacific. It was a nod to that human spirit of exploration, the same one that drives ancient wayfinders and modern cosmologists. And behind these names there are countless others, the engineers who build and maintain the radio telescopes in the deserts of Australia, the high plains of Chile. The graduate students who spend weeks writing code to clean the data, separating the cosmic signal from interference, the theorists running supercomputer simulations, testing if their models of dark matter and gravity can produce the great flows we see. It's an international effort. It needs observatories in both hemispheres to see the whole sky. It needs sharing data across continents to build a complete picture. The story of the great attractor is a human one, its curiosity pushing through frustration. It's the shared thrill when a graph finally makes sense, when it shows a river of galaxies where there was just noise before. It's collaboration on a scale that mirrors the vastness they study. These discoverers remind us the map of the cosmos isn't just points and vectors. It's a record of our collective gaze outward, a testament to the patience, the wonder it takes to find our place in the immense heaven. These maps of motion and mass, they come from numbers, from these huge tables of redshifts and coordinates, but to take that raw data and turn it into something we can feel, to let us see that river of galaxies, that needs a different kind of vision. So you have scientific artists, data visualizers. They work at places like NASA, a scientific visualization studio, or with research teams, and their job is deep. They have to take these abstract velocity fields, these gravitational potential maps, and make them into an intuitive experience. It's not about making a pretty picture. It's about building a visual language for something that's inherently invisible. You start with the real data, the precise positions and motions of thousands of galaxies from surveys like the 2-degree field. The visualizer puts all that into specialized software. They don't draw the supercluster. They ask the software to calculate the gravitational landscape that all those points of mass imply. And what you get is a 3-dimensional density map. A cloud of data points in a digital space, but a cloud is hard to grasp, so the next step is to find the watersheds. Just like water flow defines the borders of a continent on Earth, the software calculates the basins of attraction. It figures out which galaxies are flowing toward which gravitational center. And that mathematical process, that's what draws the borders of Laniakea. It outlines the supercluster not by where the galaxies are, but by where they're going. Then the artistry really starts. How do you show a flow? A common technique, a powerful one, is to use streamlines. Think of a weather map showing wind patterns. The visualizer puts a virtual camera inside that data cloud and seeds it with particles. Then they let the simulated gravity of the whole dataset pull on those particles. And the particles trace out paths. They flow along the invisible slopes of this cosmic landscape. Those paths become glowing ribbons, ethereal, rivers of light streaming through the dark. In the final animation, the galaxies are just tiny points of light, each one with a trail behind it, and those trails, they aren't random, they align. They converge, they show this great confluence, all these streams merging and flowing toward that hidden gravitational basin, down near Norma, and you see, for the first time, the shape of our immense home. Not as a static collection of stars, but as a dynamic process, a single, slow-motion whirlpool on a cosmic scale. These visualizations, they're a bridge. They take the mathematicians' equations and the astronomers' tables and give them a form our senses can hold. They let us stand outside the universe we live in and watch our own galaxy. A single speck of light carried on a current, and we see that we're part of a pattern so large it defies everyday imagination. But through this fusion of science and art, we're invited to understand it. Not just with our minds, but with a sense of awe. It makes the pull of the Great Attractor something we can finally see, and it's beautiful. The Great Attractor is more than just one mystery. It's really a way to see how we understand the cosmos. For anyone learning about space, this story pulls together almost every major idea in modern astrophysics. It starts with gravity, not as an equation, but as a real pull you can measure across hundreds of millions of light years. Gravity is the main character here. Its effects are written in how galaxies move. You can see Newton's laws and then Einstein's curvature of space-time playing out on the biggest stage. It turns an abstract concept into the plot. Then there's dark matter. The story of the Great Attractor gives the most direct evidence that what we see is only a fraction of what's there. The math doesn't work without it. That makes dark matter not just a theory, but a necessary actor. It's the hidden mountain range that explains the river's flow. For a student, that changes dark matter from a confusing idea into the essential framework of the universe. The plot thickens with the expansion of the universe. The story forces you to separate two motions, the grand, smooth stretch of space and the local drift of individual galaxies that introduces the Hubble constant. And the challenge of measuring it, it shows why the cosmic microwave background is such a crucial tool and why local peculiar velocities, like our own motion toward the attractor, complicate everything. It makes the Hubble tension not a dry problem, but a real cliffhanger in understanding cosmic history. To solve the mystery, we needed every tool. That's where multi-wavelength astronomy comes alive. We couldn't see our target with visible light, so we turned to X-ray observatories to sense the heat of million-degree gas. We used radio telescopes to listen for the whisper of hydrogen. We used infrared surveys to see through the dust. It teaches a lesson. The universe speaks in many languages. To hear the full story, you have to be fluent in all of them. Each wavelength shows a different layer of truth, and through all this, the concept of large-scale structure emerges. The Great Attractor isn't an isolated oddity. It's a natural feature of the cosmic web that leads to computer simulations, where scientists grow universes from initial ripples into vast filaments and voids. Students can see how the same simple rules of physics, run over billions of simulated years, spontaneously create structures like Laniakea and the Great Attractor. It shows science not just as observation, but as prediction and validation. Following this single thread, from a strange pattern in ancient light to the three-dimensional map of our flowing supercluster ties textbook chapters into one story. It's a story of curiosity, of technical ingenuity, of collaboration across continents and decades. It shows the scientific method in its full, messy reality. A question leads to an observation, which leads to better tools, which reveals a deeper question. For a young mind captivated by the night sky, this narrative does more than inform. It invites, it shows the biggest mysteries aren't impenetrable. They're puzzles waiting to be solved, and each solution opens a door to a universe even more wondrous. Looking for these huge cosmic structures, it's not just about mapping the sky. It builds tools, something like the Great Attractor. It's hidden behind dust. It's millions of light years across, studying something that big, that hidden. It forces technology forward. And the things invented for astronomy, they spin off. They find uses here on Earth. That pure search for understanding, it becomes an engine for invention. Think about the computing power you need to simulate how the cosmic web forms, to model the gravity of billions of dark matter particles. You need staggering machines. Projects like the Millennium Simulation, they didn't just use supercomputers. They helped drive their development. Processing those vast n-body calculations, it pushed for faster processors, better algorithms, new ways to handle unimaginable data. The techniques honed for cosmology, they're foundational now, in climate modeling, in pharmaceutical research, in financial forecasting. They teach how to predict complex systems. Whether it's a supercluster or a hurricane, then there's the data. Modern galaxy surveys, the ones that mapped Laniakea, they don't capture a few hundred points. They catalog hundreds of thousands of galaxies, each with precise coordinates, velocities, spectral signatures. Making sense of that ocean required new algorithms. Sophisticated software to find patterns, to separate signal from noise, to visualize three-dimensional flows. That work contributed directly to big data science. The same machine learning that finds faint galaxies in a noisy sky, it's used now to detect patterns in medical scans, to optimize shipping routes, to recommend a song. The Cosmic Cartographer's Toolkit, it's part of our digital infrastructure. The most direct links might be in the hardware. To see the Great Attractor, we had to look in X-rays and infrared. Building telescopes for those wavelengths meant pioneering new detectors. The CCD charge-coupled devices developed for space telescopes to capture faint X-ray photons with precision. They were adapted. Their descendants are in every hospital now. The technology behind X-ray astronomy cameras, it's fundamentally similar to the sensors in advanced medical CT scanners, in mammography systems. The drive to see hot gas in distant clusters, it directly improved how we see inside the human body. Infrared detectors created to peer through cosmic dust, they found uses. In night vision, in thermal imaging for firefighters, in quality control for manufacturing, the materials science for a mirror on a space-based infrared observatory, it often leads to better coatings for everyday optics. To more efficient solar panels, to improved touchscreens, that's the hidden dividend of curiosity-driven science. The goal was to solve a cosmic mystery. But the path forced us to invent better computers, smarter software, more sensitive eyes. The Great Attractor pulling on our galaxy, it also pulled our technology forward. It reminds you that funding the search for fundamental knowledge, it isn't just stargazing. It's an investment in innovation. The next time you benefit from a precise medical image or a complex weather prediction, remember, it might have a little cosmic dust in its lineage. Science starts stories, the Great Attractor, that name, that scale, it's moved out of papers and into fiction. In novels, it's a destination, a place for a voyage. Or a source of power. In games, it's a plot device, a hidden zone with secrets, or a threat. Online, in discussions, it gets woven into theories beyond science. It becomes a symbol, cosmic doom, a gateway. These versions are interesting. They take a gravitational thing and make it myth. The pull becomes a force with a mind. The hidden basin becomes an attractor with intent. That shift isn't a mistake, it's natural. When a science idea is deep and partly hidden, like this one, it leaves space. The imagination fills the gaps, the public adds narrative. Science shows a river of galaxies flowing toward something unseen. Storytelling gives a siren call. A destiny. Looking at these fictions tells you something about how we handle cosmic scale. The mind looks for agency, a why behind the what, so a gravity anomaly becomes an intelligence. A flow of matter becomes a planned journey. That space between science and sci-fi, it's not a problem. It's a bridge. Pop culture is a hook. It makes people ask. Someone finds the great attractor in a game or a book, then they search for the real thing. That curiosity is a start. From there, you can guide it back to the evidence. You can say the truth without a conscious will is still majestic. Not a malevolent force, but the heart of our home supercluster. Not a mysterious engine, but a sign of gravity's slow work and dark matter across billions of years. The fiction amplifies the mystery. The science deepens the wonder. If you acknowledge the stories, you meet people where their interest is. Then you can take them on the real journey, from cultural myth to a map of the cosmos, and show how the true story, our motion through the universe, that might be the greatest narrative. We have maps and models, but the great attractor still keeps its secrets. The progress is real, but it's opened up deeper questions. We're left with these open frontiers, each one a puzzle for the next telescopes, the next simulations. First, there's the dark matter. We know it's there, this invisible mountain range creating the slope we're sliding down, but we don't know its precise shape. How is it distributed in that vast basin? Is it a smooth halo, or is it clumped with its own hidden substructure? Pinpointing the exact mass, the fine details of its arrangement, that would tell us how these cosmic watersheds form. It's the difference between knowing a valley exists and having a map of every contour. Then there are the dynamics of the bright cities. We've identified the major clusters: Norma, Centaurus, Hydra, the merging heart of Abell 3627. But how do they all move? Are they orbiting a common center, or are they on converging paths, headed for a future, larger merger? Understanding their gravitational dance, the push and pull between these titanic structures, that's crucial for predicting the long-term evolution of our entire supercluster. It's like forecasting the weather for a continent by watching a few storm systems, and that leads to the next unknown. Are we missing an even larger player? Could there be structures beyond the Shapley Supercluster, so distant and immense they're adding a subtle, overarching tug to the entire flow? Our measurements of motion are always local. We can only account for the mass we can map. The possibility remains that an even greater attractor, far beyond our current surveys, could be influencing everything. The river we're in might just be a tributary to a vaster, darker sea. And of course, the Zone of Avoidance still guards its treasures. Infrared and radio surveys have peeled back the curtain, but the detailed substructure behind the thickest dust lanes of our Milky Way is still being charted. Every new, deeper survey finds hidden galaxies, hidden clusters. What major concentrations of mass are we still missing, right in our own backyard? The final census of our gravitational neighborhood isn't written yet. These unanswered questions aren't a failure of science, they're its engine. They show the story of the great attractor isn't a finished book on a shelf. It's an ongoing chapter. Each mystery is a destination for future curiosity, a coordinate for the next voyage. The map is drawn, but the territory it reveals is more complex, more wondrous than we imagined. The next part of this story is already happening. It's being built in clean rooms on mountaintops. A new set of observatories is coming. They're going to open up the great attractor's secrets. They'll map the cosmic web in a way we've only imagined. There's a spacecraft, the European Space Agency's Euclid. It's on a specific mission. It's not just taking galaxy pictures. It's doing a census, a huge, precise one. Over 6 years, it will look at a third of the sky. It will measure the shapes and positions of billions of galaxies. It uses a method called weak gravitational lensing. Light from faraway galaxies comes toward us. It passes through warped space, the space around dark matter halos. Those halos bend the light a little. They distort the galaxy shapes, like looking through a warped window. By measuring these tiny distortions everywhere, Euclid will map the dark matter. It will trace the invisible filaments of the cosmic web in 3 dimensions. It will show the real gravitational skeleton of everything. For the great attractor, this changes everything. Euclid will weigh that hidden basin. It will measure the mass of that dark matter mountain pulling us in. Then there's NAS, a Nancy Grace Roman Space Telescope. Named for the astronomer who pushed for Hubble, its field of view will be 100 times bigger than Hubble's. It will do wide, deep surveys in infrared light. That's the important part. Its infrared vision can see through the Milky Way's dust, right into the zone of avoidance. It will show millions of galaxies we can't see now. It will fill in the blank spots on our local map. We'll see the full structure of the Great Attractor region, not just the big clusters we guess are there, but the thousands of smaller groups, the connecting threads, the true density of that gravitational meeting point. Roman will also find thousands of supernovae. It will use them as distance markers to make our 3D map more precise, to better see the flow of galaxies. On the ground in Chile, the Vera Sea, Rubin Observatory is getting ready. It has an 8.4-meter mirror. It will do a 10-year survey of the whole southern sky, over and over, night after night. It will make the most detailed movie of the universe ever. This legacy survey of space and time will find tens of billions of galaxies. It will track how they move over time. For studying cosmic flows, this is different. Rubin will measure the peculiar velocities of galaxies with a statistical power that's far beyond anything before. It will see the river of Laniakea in detail. Every current, every eddy. It will probably find new, subtler flows, showing even larger structures pulling on our supercluster from farther away. Together, these missions are a leap. They take us from sketching the cosmic web to seeing it in high definition. They'll turn the Great Attractor from a shadow, something we infer, into a fully lit feature on our cosmic map. The mystery that started with a faint pattern in ancient light is about to come into sharp, brilliant focus. Looking at the bigger picture, you see the real scale of it. Our galaxy's movement isn't a lonely path. It's just one current inside a much larger structure. The universe on the biggest scale isn't just galaxies scattered evenly. It has a shape, a pattern we call the cosmic web. Think of a huge sponge, or like a brain's network but across billions of light years. The dense walls of that sponge are filaments. Long threads of galaxies and dark matter woven through space. Where those threads cross, they make dense knots. Those are galaxy clusters, superclusters. The nodes of the web, and between those bright walls and knots there are voids, huge, almost empty spaces. Hundreds of millions of light years across, where galaxies are few and it's mostly dark. That's the large-scale structure of everything. Gravity did that, working for almost 14 billion years, starting from tiny ripples in the early universe. So the Great Attractor isn't some strange, one-of-a-kind thing. It's a classic node, a major intersection in this cosmic web. Specifically, it's the main gravitational node of our home supercluster, Laniakea. That river of galaxies we're part of, that flow we measure, it's just matter moving along the filaments, draining into one of the web's big junctions. That context changes everything. The pull we feel isn't a mystery force from nothing. It's the universe's infrastructure working. The Great Attractor is a built-in part of it. A natural feature of a cosmos built this way, Our Milky Way and every galaxy in Laniakea sits on one of these great filaments. We're flowing like everything does toward the nearest major knot. Our motion is a direct readout of the cosmic geography we live in. It tells us we're not in some anonymous suburb. We're on a defined thoroughfare of the universe, heading toward a busy metropolitan center of gravity. So the mystery shifts. It's not about what's pulling us. It's about where we're located in the grand design. We're navigating the invisible topography of reality itself. Following slopes that were carved in the first moments of time, the universe leaves its clues in bent light. To measure the great attractor, we couldn't use motion. We needed something that worked on space itself. That's gravitational lensing. It comes straight from Einstein's theory. It's a cosmic scale. Mass bends space. And bent space bends light. So you have a massive thing, a galaxy cluster sitting between us and a galaxy far behind it. The cluster's gravity warps the space around it. Light from that background galaxy comes through that warped region, and its path curves. It doesn't come straight, so the image of that galaxy gets distorted. Stretched into a faint arc, sometimes smeared into multiple copies. That's strong lensing. It's dramatic, but it's rare. There's a subtler version, weak gravitational lensing. The great attractor region is huge, but it's not a single dense knot. It's vast, diffuse, so its mass creates a gentler, statistical kind of distortion. It's like looking at a street lamp through heat rising off a road. The light wavers, the image shimmers, the lamp is still there, but its shape is disturbed. In the cosmic case, the hot road is the great attractor's gravity. The street lamps are thousands of faint, distant galaxies in the background. Each one gets minutely stretched. Less than 1%, you can't see it in any single galaxy. It's buried in the noise, but if you measure the shapes of tens of thousands of the millions across a patch of sky, a pattern emerges. A statistical signal. The average shape isn't random. Those galaxies are preferentially stretched in a direction that traces the gravitational field of the massive thing in front. The Great Attractor, sophisticated algorithms analyze this sea of tiny distortions. They use it to build a map of the total mass in the foreground. Whether it glows or not, that's the breakthrough. Gravitational lensing sees anything with gravity, the bright galaxies of the Norma cluster, the hot X-ray gas, and the vast, invisible halos of dark matter holding it all together. It draws the true gravitational landscape. For the Great Attractor, these lensing maps have been key. They give independent, direct evidence of that massive overdensity hiding behind the Milky Way. They show the region's total mass is much greater than the sum of its visible parts. The distorted shapes of those background galaxies are a direct imprint, the warp in spacetime made by the attractor's gravity. By measuring the strength of this lensing signal, astronomers can weigh the whole basin. They can calculate how steep the slope of that cosmic dimple really is. This measurement comes from bent light billions of years old. It cross-checks the story told by galaxy motions. It's a different line of evidence pointing to the same conclusion. We're rolling down a hill shaped by an unseen mountain, and now we can measure the hill's incline by watching how it bends the light from the distant universe. That gravitational pull we feel is only half of it. The other half is distance. To really map the Great Attractor, you need to know not just that galaxies are moving toward a point, but exactly how far away that point is. You need a ruler, and the early universe gave us one, a ruler made of frozen sound. In the beginning, the universe was this hot, dense plasma. Matter and light were locked together. It was like a fluid, and in that fluid, sound waves could travel. They were pressure waves driven by gravity and radiation. A spot with a little more matter would pull in more plasma, but then the radiation pressure would push it back out. That created an oscillation, a sound wave ringing through everything, like a single, deep note in a bell. but this bell was the whole observable universe, and the ringing only lasted for about 400,000 years. Then the universe cooled, atoms formed, light and matter came apart, the cosmic microwave background was released, and at that moment those sound waves froze. They left a permanent mark, a spherical shell of matter, a slight overdensity, at a very specific distance from where the ripple started. The radius of that shell is the sound horizon. It's a fixed scale, about 500 million light-years across today after everything stretched. Now, fast forward. Where do galaxies form? They form more easily where there's already more matter. So galaxies are more likely to form at those original ripple points, and also at those frozen shells. This creates a subtle pattern in the large-scale structure of the universe. If you take a huge survey of galaxies and measure how they're clustered, you don't just see random clumps, you see a preferred scale. Galaxies are slightly more likely to be separated by that specific distance, the radius of that ancient sound wave, than by any other. This statistical fingerprint is called a Baryon acoustic oscillation. The bow, think of it like throwing pebbles into a still pond. Each pebble makes ripples. Those ripples expand as circles. If you could freeze the pond the instant all the ripples reached a certain size, you'd see a pattern. Every original pebble is surrounded by a ring of disturbed water at a fixed distance. The BAO is that ring, but in 3 dimensions and etched across the entire cosmos. It's a fossil of the universe's earliest music. For cosmologists, this is a gift. That sound horizon scale is a known physical size. It's a standard ruler. When we look out into space, we see this pattern projected on the sky. By measuring how big it appears to us, its angular size, we can calculate precise distances to galaxies and clusters. It's like seeing a known object, a ruler of a specific length, and judging how far away it is by how small it looks. This is how the BAO ruler applies to the Great Attractor. By using massive galaxy surveys, scientists can detect this acoustic scale in the distribution of galaxies in and around the Attractor region. They can measure the true geometric distance to the Norma cluster, to the Hydra cluster, to the heart of the flow. This is independent of their redshifts, which are muddied by peculiar velocities. The BAO gives us a clean distance. Once you have a precise distance and a measured redshift, you can do the subtraction. You can separate the part of the motion that's from the universe's expansion, the Hubble flow, from the part that's the galaxy's own peculiar drift toward the gravitational basin. It calibrates the map. It turns a blurry picture of motion into a sharp, 3-dimensional model. We can now say, this galaxy is exactly this far away, and of its total observed motion, this much is cosmic expansion, and this much is its peculiar flow toward the Attractor. This allows for an incredibly precise measurement of the gravitational potential shaping our neighborhood. The BAO ruler lets us weigh the unseen mountain by seeing how sharply it bends the paths of galaxies passing by. Without this tool, our understanding of the Great Attractor would be far less certain. We'd be estimating distances with less reliable methods, leaving more room for error in that crucial subtraction of the Hubble flow. The frozen sound waves from the dawn of time provide the bedrock measurement. They let us listen to the universe's first note and use its echo to chart the slopes down which we are all flowing. The search for the Great Attractor has become a kind of proving ground for physics. The scale of its pull, the amount of mass you'd need to create it, it tests our core theories. For physicists, this isn't just mapping a structure, it's using that structure as a lab to weigh 2 explanations for the universe's missing gravity. On one side, there's the prevailing model, cold dark matter, the idea that an invisible, slow-moving particle makes up most of the matter. Its gravity forms the cosmic web. And the Great Attractor is a dense knot in that dark web. The motions we see should, in theory, match the predictions of a universe dominated by this substance. But then there's the alternative, modified Newtonian dynamics, MOND. This theory says our understanding of gravity is incomplete, that on the vast scales of galaxies and superclusters, gravity behaves differently. It gets stronger in these low acceleration environments, so the extra pull we blame on dark matter halos might just be gravity, working by a new set of rules. The Great Attractor is a critical test. Its immense scale, that coherent flow, precise measurements of how galaxies move within Laniakea, how that motion compares to the visible mass we can map. That can distinguish between the two pictures. Is the River of Galaxies flowing because of an unseen scaffold of particles, or because gravity itself is more complex? Every new survey, every refined velocity measurement adds a data point. The hidden heart of our supercluster isn't just pulling on galaxies, it's pulling on the foundations of physics, challenging us to see if our laws hold true across the emptiness. This moves into deeper territory, a philosophical puzzle. How can we claim to know the universe when the most powerful forces shaping our place are invisible? We infer this colossal basin of attraction, not from sight but from its effects, from the subtle blue shifts and redshifts, from the statistical warping of ancient light. Our knowledge is built on inference, on reading the cosmic clues. It becomes a metaphor for the human condition. We navigate our lives guided by influences we often cannot see. Cultural currents, historical forces, unconscious biases, the subtle pull of relationships and ideas. Just as our galaxy sails toward a hidden center, our paths are shaped by a landscape of visible and invisible factors. The scientific journey to map the attractor mirrors a deeper quest. It teaches a lesson in humility, that what is most real is not always what is most apparent. Our confidence in a sun-centered solar system, in a galaxy-filled universe, each came from learning to trust the evidence over immediate appearance. Now we must trust the evidence for a cosmos woven from dark matter and dark energy. Where the bright stars are just decorations on a hidden framework, it leads to an existential thought. Our long-term cosmic trajectory, the fate of our galactic home, is dictated by forces we cannot perceive. We are passengers on a voyage whose destination is shaped by the silent majority of the universe. There's a strange comfort in that, a cosmic perspective that recalibrates our scale. The worries and conflicts of our world, while meaningful, unfold on a stage that is infinitesimally small within this grand, flowing architecture. So the Great Attractor is more than an astronomical wonder. It becomes a lens to examine the nature of reality, the limits of our perception, and our own small but curious place within an immense, dynamic, and largely unseen cosmos. It connects the work of the cosmologist to the questions of the philosopher, asking us not only where we are going, but how we can possibly know. Mapping the cosmos is now something we do together. The scale is just too large, the data too massive for any one group to handle. So astronomers have opened it up. They invite the public to help. This is citizen science. Anyone with an internet connection can join in. A project called Galaxy Zoo was one of the first. It started with a practical problem. Researchers had 1 million images of galaxies from digital sky surveys. But classifying them all by shape, spiral or elliptical, merging or not, that was impossible for any single team. The human eye is still better at that than any computer. So they built a website. They asked for help. The response was overwhelming. Hundreds of thousands of people from all over the world logged on. Teachers, students, artists, retirees. Each volunteer would see a galaxy image and answer a few simple questions about its structure. What began as a data task became a global community. Those volunteers have now classified tens of millions of galaxies. Their collective work has led to discoveries, entirely new types of objects like green pea galaxies. They've identified thousands of galactic mergers, peculiar shapes that algorithms might have missed. This crowdsourced catalog is now fundamental. It's the basis for studying how galaxies evolve, how they cluster in space. For a mystery like the Great Attractor, this public effort is essential. A big part of the search is just mapping everything, especially in the hidden zone of avoidance. So there are projects that ask volunteers to look at infrared or radio images. To mark the faint, reddened shapes of galaxies behind the Milky Way's dust, they are directly building that map. Every new galaxy a volunteer identifies, every cluster they flag, it adds a data point. It helps refine our understanding of the mass distribution in that critical region. It helps astronomers calculate the total gravitational pull more precisely. A volunteer might spend a few minutes on an image. They might circle a faint smudge, never knowing that smudge is part of a vast filament of matter flowing into the attractor's basin. But together, all those clicks build a clearer picture, a picture of our hidden gravitational heart. This changes our relationship with the cosmos. It shows that modern astronomy isn't a solitary pursuit anymore. It's not just someone alone at a remote observatory. It's a massively collaborative effort, a network that includes PhDs with supercomputers and a retiree with a laptop after breakfast. It turns passive wonder into active participation. The story of the Great Attractor, of our place within Laniakea, isn't being written by a few. It's being assembled piece by piece by a global community of observers. Every contribution, no matter how small, helps steer the course. It guides us closer to understanding this immense, flowing heaven we call home. You see a map from a Redshift survey, and it's just a sea of points. Each one is a galaxy, 100,000 tiny lights on a black field. It looks like static, a random scatter, but then you look closer and the pattern starts to come out. It's not random. The points cluster into these delicate chains. They weave into walls and into these great, sweeping arcs, and they trace out voids, these immense, spherical bubbles of near emptiness. That's the cosmic web. It's the universe's grandest visible structure, and in its geometry there's this undeniable beauty. It's breathtaking. It's the beauty of a snowflake, but on a scale so vast it's hard to even grasp. The elegance is in the repetition. You see the same branching, filamentary pattern in the neural pathways of the brain, in the root systems of trees. In the tributaries of a river delta, nature seems to have a preferred architecture for complexity, a way of building efficient, connected networks, and here it is, written across the cosmos itself. Then there are the flow maps. They take that static web and they set it in motion. You visualize the peculiar velocities, those individual drifts of galaxies, and they become streams of light. Rivers of gold and blue flowing across the darkness. They converge like water in a vast watershed. All those streams merge into the great river of Laniakea, pouring into the gravitational basin of the Great Attractor. To watch this simulation is to see a dance, a slow, stately cosmic ballet. Each galaxy is a dancer, following steps that were choreographed by gravity 13 billion years ago. The beauty here is dynamic. It's in the coherence, the way 10,000 independent motions align into a single, harmonious flow. It tells you that chaos is an illusion. Underneath, there's this profound order. These visualizations are more than pretty pictures. They're a translation. They take columns of numbers, right ascension, declination, redshift, and they turn them into a language our senses can understand. They make the invisible architecture of dark matter and gravitational potential into something we can see, something we can feel. When you look at a three-dimensional rendering of Laniakea, with our Milky Way as a tiny, glowing speck on its outer filament, you don't just learn where you are. You feel it. There's an emotional resonance, a sense of being part of something immense and something beautiful. This aesthetic experience isn't separate from the science. It is the science. The beauty is a clue. The elegance of the pattern hints at the simplicity of the underlying physics. The fact that we can capture the universe's large-scale structure with a few equations and a supercomputer suggests we're on the right track. The maps are beautiful because the universe is, in its own way, beautifully logical. The art emerges directly from the rules, and appreciating this deepens our connection to the discovery. It transforms the Great Attractor from an abstract puzzle into a landmark in a stunning, living landscape. We're not just solving a mystery. We're learning to see the sublime artwork of reality, and we're finding our own small, moving place within its frame. The discovery took about 50 years to unfold. It started back in the early 70s. Instruments on high-altitude planes picked up a pattern in the cosmic microwave background. The dipole, a hot spot in one direction, a cold spot in the opposite one. That was the first real evidence. It showed our entire galactic neighborhood was moving. We were moving at a staggering speed through the universe. That measurement was the starting point. It raised the question. Then the 80s brought an answer and a name, the Seven Samurai Team. They were looking at the motions of hundreds of galaxies. They confirmed the bulk flow. The motion wasn't random, it was a coherent river, all heading toward a specific patch of sky, a patch hidden behind our own Milky Way. In their papers, they called this unseen source the Great Attractor. The term stuck. It framed the mystery, but it was still just a direction, a point hidden behind a wall of stars. The 90s were about seeing through that wall. New surveys in infrared and radio wavelengths started to pierce the zone of avoidance, projects like the 2-micron all-sky survey. Early radio mappings, they began to reveal the silhouettes of hidden galaxies. We started to understand the attractor wasn't an empty direction, it was a crowded place. The Norma cluster came into focus as a major landmark. That was the era of first light. Our blindness started to lift. The true scale of the hidden structure began to dawn. The 2000s brought a shift in scale. Astronomers mapped the immense Shapley Supercluster far beyond the attractor. Its colossal mass complicated the picture. Was Shapley the real pull, or was it the closer, hidden mass? This decade was about refinement. Computer simulations showed such flows were natural. Massive surveys like the 2-degree field gave 3-dimensional data. They started weighing these giants against each other. The story evolved. It went from a single mystery object to a complex gravitational landscape. Then, in 2014, the pieces snapped together. A team led by Brent Tully and Helene Courtois used the motions of over 8,000 galaxies. They didn't just find the attractor's source, they mapped the supercluster it anchors. They defined Laniakea, our immense heaven. That was the culmination. It showed the Great Attractor not as an external menace, but as the gravitational heart of our own local universe. The timeline from a faint signal to a map of our flowing supercluster, it shows science as it is, not a single moment but a patient collective climb. Each decade built a higher platform, giving us a clearer view of the hidden architecture that guides our journey. The cosmos isn't just a star map, it's a way of seeing. A lens. There's this thing called the Great Attractor, an immense hidden force pulling on our galaxy, and it becomes a metaphor. It tells us to look past the visible, to sense the currents that shape things. In society, we're guided by forces just as real, often just as unseen, the slow shifts in culture, the deep tides of history. The invisible architecture of economic systems. These are social attractors. They have a gravitational pull on our collective choices, our movements. Our fates, we don't always see them directly, but we feel their effects in how ideas spread, in the direction communities take, in the quiet momentum of change. It's like astronomers inferring dark matter from the motion of galaxies. We can learn to read these forces by observing patterns, by tracing the flow of events, by looking for the coherence under the chaos. So what are the great attractors now? Maybe it's the pull of digital connection. reshaping how we communicate and belong. Or the gravitational well of a shared global challenge, like environmental stewardship, drawing nations into a new kind of collective orbit. Or it could be the enduring basin of human resilience. Where communities flow after hardship, these forces aren't conspiracies. They're not controlled by any single point. They're emergent properties, the result of countless individual actions. Countless decisions converging into a powerful stream. Our challenge is to become better cosmic cartographers of our own existence, to develop the tools. Curiosity, empathy, historical perspective, to map these invisible landscapes, to understand not just where we are, but what slopes we're on, and where the flow is taking us. This perspective invites a quiet humility. It reminds us our individual path is part of a vast, flowing system, and with that awareness comes a certain power. The power to navigate, to choose with more clarity which currents we join, and to recognize that sometimes the most profound forces shaping our journey are the ones we have to learn to see with different eyes. We started with a single strange velocity, and that led to a map of an immense heaven. Our galaxy isn't just drifting, it's moving on a current. It's one of many flowing inside this grand structure called Laniakea, the great attractor. It's not some hidden monster, it's the gravitational heart. The heart of our home supercluster. It's not pulling us toward doom, it's guiding us inside the community we're part of. That's a shift in perspective. We're not isolated spectators, we're participants in a universe that's dynamic, that's flowing. The invisible hand of gravity, shaped by the matter we see and the matter we don't, it writes the long-term story. The story of our celestial neighborhood. It's a story of connection, written across hundreds of millions of light years. This discovery, it's a testament to human curiosity, to collaboration. It wasn't one lone genius, it was generations, astronomers, engineers, citizen scientists, all across the globe. It took patience, ingenuity, a willingness to look at the universe in every kind of light. Radio waves, X-rays, each piece of data added a stroke to the portrait. Now, looking ahead, new observatories are coming. Euclid, the Roman Space Telescope, the Vera Rubin Observatory. They'll bring that portrait into sharper focus. They'll weigh the dark matter, chart the hidden galaxies, trace the cosmic web with new precision. The map of our home will get richer, more detailed. More wondrous, probably. In this exploration, there's your place in it. You are a citizen of Laniakea, living on a world orbiting a star, and that star is flowing along a filament toward the heart of an immense heaven. We are all part of this grand, slow-motion flow, witnesses to a universe alive with motion, alive with structure.